Welcome to Thought Frontier.
All right, strap in, everyone. We're going deep on celestial mechanics today. Specifically, the n-body problem, which I know you've been asking about. We've got a whole stack of stuff to dig through, even a few heavy-duty academic papers. Should be fun.
Oh, yeah, it's a real rabbit hole, the way all these objects out there, dance around each other. It's incredible.
So let's start basic then, right? When we say n-body problem, what are we even talking about?
Basically, how do you predict where a bunch of things in space, planets, stars, anything with mass, really, how are they going to move over time? And the catch is, it's all because of their gravity, each one pulling on all the others.
So it's not just like one planet going around a star nice and neat, more like a whole, I don't know, gravitational mosh pit.
Exactly. See, Newton figured out this whole universal gravitation thing, right?
Yeah.
Everything pulls on everything else. The closer they are, the stronger the pull. But now imagine three things, four hundreds, all tugging on each other. It gets crazy complicated fast.
Yeah, I can see that. So is that it? Is it just that the math gets super hard? Because we've known about gravity for a while now, haven't we?
It is hard math, no doubt. But the problem's deeper than that. Back in the day, mathematicians, they had their ways of solving things, nice formulas. But for more than two bodies, those methods they break down.
So it's like the tools themselves just aren't enough for the job.
Right. Plus, there's this whole chaos thing. You get the tiniest error in where you think something starts, and later on, your prediction's way off. Like, imagine trying to figure out where a billiard ball will end up, but it's bouncing off 100 walls first.
Okay, yeah, that's getting unpredictable fast. So if we can't solve it perfectly, then what? How do we even study this thing?
Well, we start with what works, the two-body problem that we can handle, like one planet and a star, good old Kepler's laws, nice ellipses. That's our foundation.
So break down the big mess into smaller, solvable chunks.
Exactly. But here's the catch. Even our own solar system, right? It's not really two-body. Jupiter, for example, it tugs on Earth enough to mess with our orbit a little.
Yeah.
So even with that simple starting point, we need other tricks.
I see. So what else do we have? I know our sources mentioned computer simulations. Is that where it's at?
Simulations, oh yeah, they're huge.
Yeah.
You can model all those forces pulling every which way, see how things play out over time. For few objects, not too bad, you can calculate every single pull. But galaxies, billions of stars, that gets way too expensive computationally.
So like our computers just choke on that much data.
Pretty much. We can simulate those huge galaxies, but we got to get clever, find shortcuts that are faster, even if it means a little less precision on each individual thing.
Makes sense. Now there's some more specific stuff in here too, techniques, this central configuration thing. What's that about?
Well, that's interesting. Imagine, right, you've got these objects and you arrange them just so. And if you could hold them still, then let go, every single one gets pulled straight to the center of the whole system. Perfect collapse.
Whoa, so it's like finding the perfect balance point for all that gravity.
Exactly. Studying those tells us, like, which arrangements are stable, which ones will fly apart. Gives us clues about how things evolve, even if we can't calculate every little wiggle.
That's pretty wild. Now, there's this other bit, Sunman's solution for three bodies. That sounds kind of hopeful. What's the deal there?
Sunman's work, oh, that's a classic. He found a way to actually write down the solution for three bodies as equations. Like a mathematically exact solutions. It's amazing.
So he actually cracked it. Three bodies. Solved.
He did. But there's a catch. It's insanely complex, like so messy that it's not useful for actually calculating much. And it doesn't help for more than three things. Still, it shows that even the impossible stuff, sometimes you can solve it, just maybe not in a way that's easy to use.
I guess that's still something, right? Okay, on to a different kind of three-body thing. The restricted three-body problem. That sounds simpler. What's the idea there?
That one's more specific. Imagine two big things, right?
Yeah.
Like Earth and the Moon orbiting each other. And then a third thing, much smaller, like a satellite. That model, it's super useful for spacecraft or if you've got a planet near a binary star system.
So it's like zooming in on a particular kind of three-body setup.
Yep. And that leads to this really cool concept, Lagrange points. It's like in that system, there are certain spots where all the forces, the gravity from the big guys and the little guys' own motion, they all cancel out perfect.
Wait, so you're telling me there are places you can just park a spacecraft and it stays put?
Kind of like finding a gravitational sweet spot. The James Webb Telescope, is hanging out at one of those Earth-Sun Lagrange points right now.
That's amazing. So even if we can't solve the n-body problem perfectly, we've got all these clever ways of getting a handle on it.
Oh, absolutely. And it just keeps getting deeper. There's stuff like CAM-AM theory that reveals, like, hidden patterns and stability, even in the chaotic parts. It's incredible.
All right, KM theory, you mentioned that before, and it sounds, well, kind of intimidating, honestly.
Oh, it's actually pretty elegant when you get into it. See, a lot of what we've talked about, it's about how chaotic the n-body problem is, right? Tiny change here, huge difference later. But KM theory, it's about the pockets of stability and all that. Like some orbits, they just keep going, remarkably consistent, almost like they're resisting the chaos.
Wait, really? So it's not all just random, everything flying apart? There's like order in there.
Exactly. It's like, those spinning tops. Give it a little nudge, it wobbles, but it usually catches itself, keeps spinning. KM theory is kind of like that, but for planets and stars.
Yeah.
It helps us figure out, like, under what conditions a system, even if other things are tugging on it, it can stay in that quasi-periodic motion, that stable pattern repeating over time.
So it's almost like some arrangements are just more resilient?
Yeah.
Like they've got this way of staying balanced no matter what's going on around them.
That's a great way to put it. In celestial mechanics, what it means is some orbits, they can be surprisingly stable, even with multiple bodies pulling on them. It's like finding these little havens of order within all the randomness.
Man, that's wild. It's like the universe has these rules for stability even when things look chaotic.
It really does. And that's why K-man theory is so powerful. It helps us see that underlying structure, even where we'd expect pure unpredictability.
Okay, starting to get why that's a big deal. But how does this actually play out? Like, in astronomy, what's it good for?
Well, for one, it helps us understand how stable planetary systems are, including our own, right? Are the planets going to keep orbiting the sun nicely for billions of years? Or is it all going to go haywire? K-man theory can give us clues about that. And it helps us make sense of things like the asteroid belt, why some areas have way more asteroids clustered together.
So it's not just theory, it's actually useful for figuring out the universe around us.
Exactly. It shows this amazing balance that governs all those motions, and even with something as simple as gravity. There's just so much complexity and beauty to it.
I'm with you there. This is fascinating stuff. Now, I noticed our sources also dive into this four-body problem specifically, and there's this talk of coplanarity. What's that all about?
Yeah. That's some really cool recent research. Four-body problem, you guessed it, four objects and their gravity. What they found is, for certain types of these systems, there'll always be a moment when all four objects line up in the same plane.
Wait, seriously, so no matter how they're moving in 3D space, they'll always, like, flatten out at some point?
That's what the research shows. It's for systems where the total angular momentum is zero, basically a measure of how much the whole thing's spinning, and the motion's got to be bounded. They can't just fly off to infinity. But if those conditions are met, no matter how complex the dance is, you get those moments of coplanarity.
That is so cool. It's like there's this hidden choreography making them line up.
Exactly. And to make it even more interesting, those coplanar configurations, they can take different forms, different geometrical arrangements. So now the question becomes, can we predict which one comes next? Can we crack the code of that dance?
So it's not just knowing that they align, it's about the order, the pattern of it.
You got it. The researchers even talk about using symbol sequences to represent those patterns, like creating a code for the four-body problem. It's really exciting stuff.
Okay, so we've gone from the n-body problem in general to CAM theory, now this coplanarity thing. It's getting pretty abstract, but I gotta ask, is there a connection to stuff here on Earth? Like, does any of this have applications beyond astronomy?
That's a great question. It might seem surprising, but yeah, the n-body problem, the math behind it, it pops up in all sorts of places. The equations, they're similar to what you see in statistical mechanics, even machine learning.
Whoa, really? So trying to figure out how planets move could help us with, like, self-driving cars or something.
Sounds crazy, but it's true. It's all about optimization, right? Finding the best, most stable way for things to work together within a complex system. And some of the techniques we use for the n-body problem, they can be applied to those other fields too. Like machine learning, you're trying to find patterns in data, make predictions. Turns out, some of that celestial mechanics math is really helpful for that.
So there's this hidden link between how stars move and the algorithms running our technology.
Exactly. It's a beautiful example of how different areas of science, they connect in these unexpected ways.
This has been a wild ride so far. Before we wrap up, though, there's one last thing from our sources, this shape space for the four-body problem. What in the world is that?
Yeah, that's one of the more mind-bending parts. Shape space, it's a way to represent how the four bodies can be arranged. But instead of their actual positions and speeds, it's all about the geometry, like the shapes they make relative to each other.
So it's like stripping away all the movement and just looking at the pure shapes they create.
Exactly. And get this, the shape space for the four-body problem, it has this really elegant mathematical structure. Turns out it's homeomorphic, meaning it has the same basic structure as six-dimensional Euclidean space.
6 dimensions? Okay, now you're really losing me. I can barely picture 3.
I know, it's tough to visualize. But the point is, even when we ignore all the details of how they're moving, the possible arrangements of those four bodies, they have this hidden, beautiful structure. It's like a blueprint, but in a higher dimension.
This is all incredible, but I gotta ask, what's the point of knowing about this shape space? Does it actually help us solve the four-body problem?
That's the big question, isn't it? It's like being given a map to a treasure, but you're not quite sure how to read all the symbols yet. Researchers are working on that. Understanding this shape space, it could give us totally new insights, maybe even lead to solutions we haven't even thought of.
So it's like a whole new frontier to explore.
Exactly. And we're just at the beginning. There's so much more to discover, so much more to understand.
Man, my head's spinning a little bit, but in a good way. This whole N-body problem, it's way more than just planets and stars, isn't it?
It really is. And I think it connects to all these other fields, too. That just blows my mind. Like, studying the universe can help us build better algorithms, even understand complex systems here on Earth.
Oh,
Crazy.
it's amazing, yeah. And this whole shape space thing, the structure hidden in there, that's really stuck with me. But I gotta be honest, it's pretty abstract. You really think figuring that out will actually lead to any breakthroughs? Like, will it help us solve the four-body problem for real?
You know, it's hard to say for sure, but I think the potential is there. It's
Yeah.
like, I imagine we've got this incredibly detailed map, right?
Mm.
But we're still figuring out what all the symbols mean. It'll
Yeah.
take time, but exploring that shape space, it could give us totally new ways to think about the problem, maybe even solutions we haven't even imagined yet.
So like a whole new frontier in celestial mechanics.
Exactly. And the best part is we're just at the beginning of that exploration. So much more to discover, so much more to understand.
Well, this whole deep dive, it's really been an eye-opener. The universe is just so much more complex and fascinating than I ever realized.
Couldn't agree more. And what's really cool is that every new discovery, it seems to just lead to more questions. You know, it's like this never-ending journey of knowledge.
I love that. Well, I gotta thank you for taking me on this incredible journey through the N-body problem. It's been a real privilege.
The pleasure was all mine, really.
Yeah.
And for everyone listening out there, if this has sparked your curiosity, don't stop here. There's a ton of resources out there. We'll put some links in the show notes.
Yeah, go explore. The universe is full of mysteries just waiting to be uncovered. So keep asking questions, keep that curiosity alive. Who knows? Maybe you'll be the one to make the next big discovery. Until next time, keep looking up.